After having shown the structural basis of the parietal additions, let us continue the description of the elements of average mass.
With sulfur, we have 4 stable isotopes. The first is sulfur-32, which corresponds to the second complete layer of the hexahedral morphology, which is therefore well balanced. With 3 internal pentagons distributed over the lobes H6 of the equator, we obtain the sulfur-33. Now, with sulfur-34 we move to tetrahedral morphology with 2 additions H12 on the 3rd layer. Each of the 2 additions is then supported by internal triple helices. Finally, with sulfur-36, the nuclear wall is now wide enough for 2 parietal reinforcements in the equatorial dodecahedron mode to develop and offer solid support. In this way, the sulfur-36 represents the second dodecahedral layer. Now, before examining the chlorine, let us describe the last type of parietal addition. Thus, at the equatorial level on the 3rd layer of the hexahedral morphology we have hollows of 10 pentagons. They then fill with 2 lobes of 6 pentagons. Therefore, one H10 addition leads to an additional of 2 pentagons on the parietal surface. It then takes 3 H10 additions to obtain an increase of 1 electrical charge with 2 mass units. With the element chlorine, we have 2 stable isotopes. The chlorine-35 is structured from the hexahedral base of sulfur with 3 additions H10 at the equatorial level with 3 internal pentagons, to ensure good rigidity. For chlorine-37, we have 3 H12 additions on the 3rd tetrahedral layer. Each group H12 then has an internal triple helix, to stabilize the parietal assembly. Argon has 3 stable isotopes, and represents the 3rd complete layer of tetrahedral morphology. Well balanced and without internal propellers, it is argon-36. With 2 internal propellers it is argon-38. And with 4 internal helices it is argon-40. Note that an odd number of propellers is a factor of imbalance. Like chlorine, the potassium element has 2 stable isotopes. In the tetrahedral base, potassium-39 has 1 H12 addition on one of the 4 summits of the 4th layer with an internal stabilizing helix placed opposite to balance. While the potassium-31 on hexahedral base with 2 H12 additions on the 2 poles in the 4th layer. Each of the tetrahedral polar additions has an internal trefoil, while the 3 equatorial additions H10 have an internal pentagon. With the calcium element there are 5 stable isotopes. Note that the calcium isotope 40 is the last nuclide without internal parietal reinforcements. Calcium-40 corresponds to half of the 4th tetrahedral layer with 2 H12 additions. Similarly, Calcium-32 resumes this morphology with 2 internal trefoils under the 2 new H12 addition. With an odd number of mass units, Calcium-33 is of hexahedral morphology with 2 additions of type H4 on the equator, and with 2 internal trefoils under the 2 poles. Now, starting with Calcium-34, we have the possibility of positioning 2 dodecahedra in equatorial reinforcement and in opposition as for Sulfur-36, with the possibility also of adding trefoils under the additions H12 into the layers 3 and 4, but in even number. This gives Calcium-36 and Calcium-38. However, the limit of flexibility of the wall is reached because the Calcium-50 is unstable. Now, with the scandium, we find again the singularity of the odd numbers. The scandium-45 is the only stable isotope presenting a balanced form and hexahedral morphology with 3 additions H4 at the equator. Stability is allowed by 2 polar clovers and 3 equatorial interpentagons. With the titanium element we also have 5 stable isotopes. Titanium-36 corresponds to the 4th complete tetrahedral layer. It is stabilized by 2 opposing internal trefoils, each under the 3rd and 4th layer. The Titanium-38 and the Titanium-50 also integrate in this morphology with internal trefoils distributed evenly under the whole of the wall. But the Titanium-38 also possesses an isomass and dodecahedral morphology of which it forms the 2nd layer after magnesium. It is then solidified with 2 equatorial dodecahedrons in diametric opposition. Concerning the hexahedral morphology, let us note that a concavity of 6 pentagons is automatically transformed in convex form. Thus, with 3 additions H4 on the wall of the scandium, we obtain a form inflated at the equator of 135 external pentagons, and consequently an electric charge of 22. With 2 internal trefoils under the 2 poles we obtain the Titanium-37. And with a polar clover and 3 clovers under the opposite tropic we have Titanium-39. Note that the Titanium-52 is unstable, which shows the limits of flexibility of these morphologies. The vanadium element has only 1 stable isotope. It takes up the morphological basis of Titanium-39 with a solid dodecahedron H3 on the pole with a tropical distribution of 3 internal helices. Now, chromium shows 4 stable isotopes. Chromium-50 represents the 5th complete tetrahedral layer with 6 H10 additions. The wall is solidified with 2 diametrically opposed internal helices. Similarly, on this morphological basis the chromium-52 has 4 internal helices. and chromium-54 has 6 internal helices, 3 under the 4th layer, and 3 others under the 5th. For chromium-53 we find the hexahedral morphology by taking the base of vanadium-51 with 2 additions H3 on the 2 poles. The solidity of the wall rests on 3 internal equatorial helices. For the manganese element, we find a unique stable isotope. The manganese-55 is in the hexahedral form of chromium-53 with 2 additions H4 on the equator in diametric opposition, with 2 trefoils and 2 internal pentagons. Iron has 4 stable isotopes. The iron-54 relies on the form of the tetrahedral chromium-52 with 2 additions H3 in diametric opposition, 1 on the 5th layer and the 2nd on the 4th. Iron-56 represents 4 H3 additions on the 4th tetrahedral layer. The iron-57 takes up the hexahedral base of the manganese-55 with 3 additions H4 on the equator with the adapted internal reinforcements. And the iron-58 has 2 additions H3 on the 5th tetrahedral layer with 4 inner helices under the 4th and 5th layers.
With the elements cobalt, nickel, copper, zinc and gallium we reach the limits of the agglutinative synthesis. It should be noted, however, that among the latter's, nickel-60 represents the 5th tetrahedral layer with 4 H3 additions, which provides a very symmetrical form of zero spin as for iron-56. But we reach the maximum permissible expansion of pentamorphic flexibility.
Beyond that, the nuclear wall will crack, and agglutinative synthesis stops at this point.